This is lecture 17. Today we'll be talking about valence bond theory. So we'll be starting to talk about the electronics that are going on inside molecules. Now, this isn't the greatest theory. It is actually a subpar theory. We have a better one that we'll go over next time. But the correct theory, molecular orbital theory, is actually pretty complex. So we still learn valence bond theory because it's a lot easier to do. Let's say we need to figure out something quick, but don't need a super detailed explanation of what's going on. This valence bond theory comes in handy. So this theory comes to us by Linus Pauling, who is an American chemist and biochemist. And what Linus said, or Dr. Pauling said, was that bonds likely form when you have orbitals from two different atoms, and those orbitals overlap. It's pretty simple, right? We've already got the electrons doing something. What happens then if these electrons just now do that same thing in the same place with electrons from other atoms? Of course, there's some rules here. For starters, only half-filled orbitals can participate, right? We have to have an unbonded electron or an unpaired electron that's going to then pair with an electron from a different atom. And our orbitals have to have the proper shape and orientation to overlap. So they have to be pointed at each other and have some region where they can actually touch. So this overlap can happen between two s orbitals, such as in H2. It can occur between an s orbital and a p orbital, like what happens in HCl, or it can happen between two p orbitals, such as in Cl2. And of course, these are all just diatomic molecules, but this is kind of thought of as what's going on in other molecules as well. So when we get this overlap, and it's in the axis of the atoms here, or of the nuclei, we call this a sigma bond. So sigma bonds are these head-to-head overlaps, so you don't have any angle between the two nuclei and the bond in between them. So this can happen between s and s orbitals, s and p orbitals, or p and p orbitals, or some more complicated orbitals, as we'll find out in a little bit as well. So like I said, these sigma bonds, they have all their bonding going on between the two nuclei. So after you form a sigma bond, if you have some extra electrons and orbitals left over, then you can start forming what are called pi bonds. So these pi bonds are more side-to-side overlap. So in these, let's say you have a p orbital sticking up and down from your atom, and your other atom has a p orbital sticking up and down. Then those two p orbitals can lend electron density to each other and form this pi bond. So whereas a sigma bond has its electron density along the axis, the pi bond has a node along the axis, and so all its density is either going to be above and below the axis or on the sides of the axis. So pi bonds are how we get double and triple bonds. So first we have to form that sigma bond, and then we can get the pi bonds. So another way of saying that is you can't have pi bonds in a region where you don't already have a sigma bond. Okay, let's look at some of these orbitals overlapping. So this is just a visual demonstration, right, of what's going on, and we're going to spend most of this time, most of this lecture talking about single bonds. Pi bonds are really just those p overlaps. But here I'm looking at H2. I've got the electron configuration of one of the hydrogen atoms over here, the other hydrogen over here. You notice these each have an electron and these 1s orbitals. And so we can think of these orbitals as overlapping, and then this overlap, right, is our sigma bond. So this is the case for two s orbitals overlapping, but then if we had something like hydrogen fluoride or hydrofluoric acid, more properly, then the hydrogen would have a valence electron in the 1s shell, the fluorine would have a valence electron in the 2p orbital, and these guys would then overlap, and the density in between, again, would be that sigma bond. So here, right, you can get this sigma bond between s orbitals, between s and p orbitals, and between p and p orbitals, etc., whatever you need to get the job done. Let's see real fast how you're dealing with all of this. So the sigma bond in hydrobromic acid is formed by the overlap of what? You can go ahead and pause here and try and figure this out. All right, is it a p orbital on hydrogen and a p orbital on bromine, an s orbital on hydrogen and a p orbital on bromine, a p on the hydrogen and s on the bromine, an s on hydrogen and an s on bromine, or sp orbital of hydrogen and an sp orbital on bromine? Well, if you don't know what that last one means, that's because I haven't taught it to you yet. But for this problem, right, we need to figure out which orbitals are being occupied in each of these, in each atom. So hydrogen, of course, is going to have its valence electrons in the 1s orbital. So it's going to be an s orbital on hydrogen. So our answer is going to be either B or D. But then with bromine, we have to figure out its electron configuration. It's coming in with 7 valence electrons, right? So the first 2 of those are going to be in an s orbital, and then it's going to have 5 electrons in p orbitals. 2 of those p orbitals are going to be filled with paired electrons, but the last is going to be an unpaired electron in a p orbital. So the answer here is going to be B. We're going to get overlap of the s orbital in hydrogen and a p orbital in bromine. So that's the original valence bond theory, but Linus Pauling quickly ran into some issues with his theory. The first, we can illustrate with beryllium dihydrogen. In this molecule, we have beryllium forming 2 bonds, but beryllium's valence electrons are these 2 paired electrons in the 2s orbital. So how are you going to get these 2 paired electrons to actually bond? If they're already paired, why would they pair with something else? And moreover, how do you get a linear shape from this? And then the next problem kind of follows along with this. In CH4, like I'm showing you here, this guy has bond angles of 109.5 degrees. How do you get angles of 109.5 by overlapping a sphere and then these orbitals that are all along the axes, right? If you take these, that would predict all your bonds would have to be, 90 degrees away from each other, not 109.5. So I guess either 90 degrees or 180, but certainly not 109.5. So what's the solution to this? Well, the solution is we're actually going to create hybrid orbitals. So the idea here is you just take your available atomic orbitals and you mix and match them to get your hybrid orbitals. And so the idea here is every atom has its own hybrid orbitals, right? We're not talking about a hybrid orbital between carbon and hydrogen. So carbon would have its orbitals, hydrogen would have its orbitals. But if we're going to get something like beryllium dihydrogen and we need a 180 bond angle, then we're going to need 2 bonding orbitals, right? One to hold one hydrogen on, one to hold the other, and we're going to have to explain why they're 180 degrees apart. So we're just going to mix 2 atomic orbitals on beryllium to get these 2 new hybrid orbitals. So let's look at what that looks like in terms of electron configuration, right? So beryllium has these 2 paired electrons in the 2s orbital. But then what we're actually going to do is we're going to, since we need 2 orbitals, we're just going to take 2 of beryllium's orbitals, kind of mush them together, and then divide that mush into half. So now what we're going to say is we're going to have two sp orbitals. So we took one of the p orbitals and the s orbital, combined them to get 2 sp orbitals. And then we have 2 leftover 2p orbitals. And you'll notice the way I've drawn this, the leftover p orbitals are slightly higher in energy than the sp orbitals, so the electrons are just going to stay in these sp orbitals. And then these can overlap with the s orbitals in the hydrogen. So you'll notice though, when I was done hybridizing, I was left still with 4 orbitals, and I started with 4 orbitals. So you're always going to keep that same number of orbitals around. Okay, but it probably looks like what I just did was completely random out of left field. So let's talk about how we mix orbitals. And first, let's make some sp orbitals and show how they're going to give us our 180-degree geometry. So this is the idea. We're just going to take an s orbital, and we're going to combine it with a p orbital. Now you'll notice in this p orbital, we've got a red region and a blue region. What this corresponds to, remember these are three-dimensional waves, and the wave has an amplitude. Sometimes that amplitude is positive or above zero, sometimes it's negative below zero. So the blue part in here would signify the positive region of that wave, and the red part would indicate the negative region. So the s orbital is all positive. So when we mix this s orbital with the p orbital, we're going to get a region of destructive interference, where there's red on the p orbital, and constructive interference, where there's blue on that orbital. So we put those together, and we get an orbital like this, the sp orbital. But when we've done this, right, you'll notice we took two orbitals, we got one out. That seems to have violated our conservation of orbital rule. So we're actually going to have to make another one. And the way we're going to do that is actually by taking this s orbital and subtracting our p orbital. So the first one we did s plus p, and then the second one is s minus p. And you might ask, well, why are you subtracting the p and not the s? And the answer is it actually doesn't matter which one you do. So if I did s plus p and p minus s, you'd end up actually with the same result. Because when we're subtracting this p, what that means is we're actually going to flip the signs on the two regions here. So you can think of this red lobe as now becoming blue, and the blue lobe is becoming red because of that negative sign. So when we subtract here, we're going to get constructive and destructive interference in opposite regions, and so it's going to look like this. But now, since we've constructed this from our two p orbitals, from our p orbital that's stretched along an axis, our two new sp hybrid orbitals are also stuck on that axis, and they're going to be stuck 180 degrees apart. The interesting thing is, you'll notice they have this big region of density and then a little small bit of density on the other side of the nuclei. And so these, they just get this fun overlap. So to give you another visualization of this, if I have this s orbital denoted by this clear, slightly bluish circle, and then I've got my three p orbitals denoted with the yellow balloons, and you'll notice I have my energy levels here as well, so my s orbital is lower in energy than my p orbitals. Once I hybridize, then our image changes quite a bit, and now each of these red balloons you can basically think of as an sp hybrid orbital. And so it's got this linear geometry, and it's got these two unfilled p orbitals here that may be available for pi bonding if we have some leftover electrons. All right, so how though, right, do you say how you hybridize these orbitals? Well, the answer is that both lone pairs and single bonds in an atom need hybrid orbitals. So let's say you have a steric number of 3, then you're going to need 3 hybrid orbitals. Or in other words, you're still just going to draw a Lewis structure. You're going to find your steric number on your Lewis structure, and then you're going to make enough hybrid orbitals to match the steric number. So if you have a steric number of 3, you'll need 3 hybrid orbitals. What do I mean by that? Well, let's start with a steric number of 2. That'll give us this sp hybridization we already saw with beryllium hydride. You'll notice that in this hybridization name, we've got 2 letters, S and P, right? And that's going to give us 2 orbitals, right? And the hybridized orbitals are just these purple lobes. But let's say we have a steric number of 3, then we're going to need 3 letters in our hybridization, right? And if you remember, with the S subshell, there's 1 orbital. With P, there's 3, right? You got your PX, PY, PZ. And then you've got your D subshell, which has 5 orbitals in it. And so basically we're just going to steal from these orbitals in order. So if I have a steric number of 3, I'm just going to count SPP. All right, and so that'll be my hybridization. We'll call that SP2. And that'll give us this trigonal planar geometry. Now, for these more complex hybridizations, you don't need to know how to add and subtract orbitals, etc., to get these combinations. Just know that some physicist or physical chemist worked that out for you. Right, but let's say you have a steric number of 4. You're going to need SPPP, so you're going to need an SP3 hybrid orbital. And since we're taking 4 orbitals to make that, we actually end up with 4 of these SP3 orbitals. If you need 5 orbitals, you're going to make SPPPD, so an SP3D orbital. And of course, if your steric number is 6, you'll go SPPPDD, and you'll get this SP3D2 hybridization. Well, I rushed through that just to make sure we get all that on the table. Now we can spend the rest of this lecture, or almost the rest of it, just looking at this hybridization and how it works. So we'll back up. So we've already looked at the SP hybridization, but let's back up and look now at the SP2 hybridization. So an example of where this happens is in boron trifluoride. So the central boron, it has 3 single bonds, or it has a steric number of 3, right? It's got no lone pairs. So we're going to need to make 3 hybrid orbitals. So we're going to take SP and P, we're going to combine those to get these SP2 orbitals, and we'll have 1 leftover P orbital that's slightly higher in energy. So this will give us our trigonal planar geometry here. With the SP3 hybridization, so this would correspond to something with a steric number of 4, like carbon in this methane molecule. So methane is CH4. So here, right, steric number of 4, we got 4 atoms attached, no lone pairs. So we're going to need to take 4 of these orbitals and hybridize them. So we'll take our S, P, P, and P. We'll get our 4 SP3 orbitals. You'll notice that all 4 of these SP3 orbitals are degenerate, right? They have the same energy here. And this will give us a tetrahedral geometry. So with this one, you can just trust that we combined the S and the P orbitals in some strange magical way that got us these bond angles. And it is a little complicated. So if you really care about that, you can go on and take quantum mechanics in the future. But now SP3D, this hybridization where we have the steric number of 5. So an example of where this occurs is in SF4. So in SF4, your sulfur has 4 bonds, or 4 single bonds, and a lone pair back here. So we're going to need to make 5 hybrid orbitals here. The problem is, right, you only have 4 valence orbitals. You've got your S and your 3p orbitals, but here we're actually going to have to dip into our d orbitals. So our d orbitals are going to take part in this hybridization. So we'll take the s orbital, 1, 2, 3 of the p orbitals, and just 1 d orbital. So that will give us 1, 2, 3, 4, 5 orbitals to combine to give us 5 hybrid orbitals, our sp3d hybrid orbitals. And you notice we'll get 5 of those because there are 5 letters in the name, or 5 orbitals were hybridized. And then we'll be left over now with only 4 d orbitals besides that. And you'll notice here in the electron configuration, we've also got our paired electrons, which we can see on the back of this sulfur here, right? So it all kind of works out, and it gets us this trigonal bipyramidal electronic geometry. And the last thing that we need to worry about is the sp3d2 hybridization. So this occurs for things like sulfur hexafluoride, or SF6. So here sulfur is bonded to 6 different things. So we need to get all of these bond angles. And so here, again, we're just going to take an s orbital, p orbital. sorry, an s orbital, 1, 2, 3 p orbitals, and then 1, 2 d orbitals. That'll give us a total of 6 orbitals that we can use to hybridize, and we'll have sp3d2. So now Linus Pauling didn't just throw this stuff out. He also did all the math that gave us these crazy geometries and so forth. So he does deserve quite a bit of credit for all of this. And this idea really helps us to figure out bond angles or explain what's going on with bond angles, etc. So let's see if you're following what I'm laying down here. Give me the hybridization of bromine in BRF3. So BRF3 is one you should have drawn in your homework last weekend. And tell me what the molecular geometry of BRF3 is as well. All right, so you can go ahead and pause this if you'd like right here. So the steps you're going to need to take are 1, draw the Lewis structure, 2, find the steric number, 3, make enough hybrid orbitals to match the steric number, and then of course 4, ignore lone pairs when you're naming the molecular geometry. So if you need to pause the video again, go ahead and do that and try and figure this out. All right, you should have gotten a Lewis structure that looks like this, with bromine in the center, connected to 3 fluorines, and bromine should have 2 lone pairs on it. So this would correspond to a steric number of 5. So our hybrid orbitals need to have 5 letters in it. So that would be S, P, 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 D. So our hybrid orbitals need to be sp3d. So our answer is either going to be B or D here. Those are the only ones with the sp3d hybridized orbitals. Now we need to figure out then what's the geometry around this. Is it going to be either B, trigonal planar, or D, T-shaped? Well, we only get trigonal planar when we have a steric number of 3, right? In this case, we're going to take off the, we've taken the atoms off of the equatorial locations, or in other words, the lone pairs on the equatorial locations. So these 2 fluorines are in the axial positions, roughly 180 degrees apart from each other and 90 degrees from this equatorial fluorine. So the answer here is going to be a T-shaped molecule. All right, so that's it for hybridization. It's a funny thing that seems complicated until you get it down, and then it seems fairly straightforward. But as you can see from a problem like this, right, you still have to do a lot of steps to get there. And if you mess up on any of these steps, it can cost you. So the best thing to do, right, is just to find practice problems and practice them over and over again until you get all those steps down. Because the last thing you want to be doing is stepping on your own feet here. So now that we've talked about hybridization, let's turn our attention now to some double bonds. So hybridization really only deals with sigma bonds. All the sigma bonds are, or hybridization only happens for these sigma bonds. So when we get into double bonds, like here in ethene, so in this molecule we have 1 sigma bond between the carbons and 1 pi bond between the carbons. And of course we have some sigma bonds to the hydrogens. But so what's going on here is these carbons, right, they have a steric number of 3. So they're going to have sp2 hybridization around them. So we're going to get this sp2 overlap in the center, but we've also got these p orbitals that haven't been hybridized. And now they're sticking up, as I'm showing you here in this picture, they're sticking up and down out of the plane of the rest of the molecule. And so then these 2 p orbitals will hybridize. So, or sorry, they won't hybridize. They will not hybridize. They will overlap and you'll get a bond. Now these pi bonds you can see have some density above and below this plane of the molecule. And a similar story is going on when we have a triple bond. So for example, in ethyne, in this case, you have 1 sigma bond in the middle and 2 pi bonds between these 2 carbons. In this case, the carbons have a steric number of 2, and so they have this linear geometry. And so if you have a steric number of 2, your hybridization is going to be sp. So you're going to get 1 sp orbital on each carbon overlapping here in the center. Of course, they'll also have these sp orbitals overlapping with the s orbitals in hydrogen. But then you have these unhybridized p orbitals, either sticking above or below the carbons or sticking out to the left or right of the carbons. And so the ones sticking up and down, those will overlap with the up and down or p orbitals from the other carbon to form a pi bond above and below this molecule. And then the p orbitals that are sticking out left and right will also overlap, and we'll get a pi bond that's on the left and right of this molecule. So in that case, you're getting two pi orbitals, or two pi bonds, sorry. So you'll notice in this geometry, though, we've only got these p orbitals sticking up and down or side to side. Because of this, and because of this whole hybridization idea, we actually never have three p orbitals that are left over for bonding. So there's not actually any way to do that. The reason I'm saying that is there's actually not a reasonable way to get three pi bonds in a single system. And it's this geometry limitation that limits us to only single, double, or triple bonding, which is pretty interesting. So now you're getting a real good image of the electronics of our molecules, right? What's going on with the electrons that's causing this bonding to occur. All right, so that is valence bond theory. The advantages of the valence bond theory is it takes atomic orbitals into account in bonding, gives us a way of predicting bonding here, and it focuses on individual bonds and molecules, so it's easy to apply. Even over a big molecule, let's say a molecule with 50 atoms, you can still figure out the hybridization around each atom, because you're just going to look at each individual atom, say what's its steric number, and figure out its hybridization, etc. And it explains the shapes of our molecules using hybridization. And there's mathematical backing behind that, which we didn't go over and we're not going to go over in this class, but it's there. Now the disadvantages, though, to valence bond theory is it doesn't predict bond energies. So there doesn't seem to be any direct correlation between which hybrid orbitals are being used or non-hybrid orbitals and how strong a bond is, or specific bond. And it doesn't explain the magnetism or the absorption emission spectra of molecules at all. It doesn't even touch on that. And it doesn't explain the delocalization of our pi bonds. So as we just saw, we've got these p orbitals that are overlapping, but really that should just give us a centralized pi bond, whereas for delocalization and all these other issues, we're going to have to turn to a much more complicated and dynamic theory called molecular orbital theory, which we'll get into next time.